In this class, we are going to talk about computer-aided data acquisition. As you know, previously when we talked about signal analysis, particularly finding out the features of the signal, be it the RMS value, be it the mean value, we had certain integrations to be done where we required a mathematical function for a signal. As simple as that, suppose I want to find out the mean of a signal, I need to integrate the signal over a time period. Okay. But the problem there lies that if I have a signal of this nature which is coming out of my machinery, I do not have an expression or a mathematical equation to this curve. If it was a nice sine wave where x t was equal to a sine omega t, I am sure all of us have done such integrations even in our first year electrical circuit courses, and we are very happy and comfortable to find out features of the signal. Okay. But then this could be done in a better way. Instead of x t representing this signal, I have closely spaced point x I. So, if I have such sequence of x I can analyze them like nothing but I is equal to 1 to n divided by n. Okay. So, this is a simple example how if we have this as an analog signal, and here I have a digital equivalent of that signal. Okay. So, the job of us right now is to how to convert this analog signal into a digital signal, so that all this numerical computations, be it just finding out the features, even finding out the frequency domain, coefficients of such signal, we can do that, and that is actually what is done in digital signal processing. And just to recap, as you know, in CBM, our machine's condition actually depends on what we infer from the signal obtained by this transducer x t. Okay. What do we understand from this signal x t? And so, that is why we have a nice module of signal analysis. Okay. But to do any mathematical signal analysis or DSP, I need to convert this signal from analog to digital. So, this is what we are going to focus on in today's class. So, data acquisition is values which are discretely sampled in time. Discretely means there is a definite time interval between the signals. So, this delta t is known as the sampling interval. A device, a hardware device does this. So, it will give you a corresponding analog value to this discretized signal x t. Okay. And that is this hardware which we are going to talk about. And then another quantity is resolution. What is the minimum value the signal can be sensed? I will give you an example here, because see all the signals which are digitized, I have an analog domain and then I have a digital domain. So, in analog domain I have a analog voltage may be from 0 to 10 volts. This is my transducer output. Certain transducer gives me maximum value it can give from 0 to 10 volt analog signal. Okay. But then once I do an A to D conversion, I should be able to store this in digits. As you know, in digital domain, I can store a value either as a 0 or a 1. So, there are two options. So, if this is a 2 to the power 3 bit for the sake of discussion system. So, the possible values of zeros this guy can have is all the from 0 0 0 to 1 1 1. So, I will have 8 values. Okay. So, whatever be the analog signal which is coming to the system, my A to D is only being able to convert into digital values and only have 8 positions or locations to store this value. So, this amplitude resolution is nothing but your total voltage. So, in our case 10 volts divided by 2 to the power 3, 10 by 2 to the power 8 is 1.25 volt. You see, this bit size plays an important role in the resolution of this A to D converter. So, one thing we have to keep in mind, one is the sampling interval. I will give an example of the sampling interval, and other is the bit size, apart from few other things. So, today if I go to buy a hardware for the analog to digital conversion, these are the two important features one has to look for, or the specifications. And by the way, sometimes the sampling interval is related to the sampling frequency, F s is nothing but 1 by delta t. Okay. So, this also creates another problem. Imagine I have an analog signal of this nature, and I sample at few points shown by this red dots. That means what? I am picking values equally spaced sampling intervals. So, if I join this red dots, I will get my original white signal. But instead of delta t, suppose I pick another sampling interval at a different sampling rate, one is this x, and so on. So, you see, if I join this, I am getting a straight triangular wave. So, and this is the new sampling interval, delta t star, where delta t star is greater than delta t. So, I have got this a triangular wave. As opposed to the original sine wave. So, I have created by inadequate sampling frequency, I have created or aliased or made a signal wrongly represented in the frequency domain. Okay. I will continue this discussion, but just to tell you, this analog to digital conversion methods, there are two methods. One is the flash conversion and other is the signal delta conversion. We will not go into the details of this, just to know that when you specify, you have to specify either of these two processes. So, the errors because of data acquisition, one is the sampling error, which we discussed, is known as signal aliasing, and other is the quantization error because of the inadequate resolution. I will explain it through a better diagram here. So, if you see here the same signal, this is my black line, continuous line in the original signal. Okay. Now, because of a defect in this machinery, I have got some glitches in the signal, which could be because of some machine faults, and this has to be captured by me. But if you see, if I have a 3-bit computer, so these are the actual values 0000 to 111. So, if I have the amplitude resolution, this is nothing but 10 divided by 2 to the power 3 or 10 by 8 is 1.25. So, the data acquisition system only understands 0 to 1.25, 2.5, 3.75 and so on volts. So, in this case a 5 volt analog signal is represented by this line, and the next point it comes here, which is only 6.25. So, it is not able to decide the minor variations between 5 to 6.25, because the least it can sense is only 1.25. So, in that token what I get is a jagged wave like this, which is my digital representation of my analog signal, which is quite different. Well, how could this be improved? This could be improved if I had finer resolutions. So, this amplitude resolution which I am talking about is nothing but the maximum range by 2 to the power n, where n is the bit size. If maximum range was 10 volts and for 3 bit we saw this as 1.25 volt. Okay. If I increase this in bit size, 2 to the power 4, okay, 16, 2 to the power 5, 32 and so on. Okay, this is with increasing bit size, the denominator increase. So, this will reduce. So, one way to improve this amplitude resolution is to reduce the quantization error. So, quantization error in a data acquisition system can be reduced by increasing the bit size. So, if you see the numerical accuracy of a 12-bit laptop is less compared to a 24-bit or a 32-bit or a 64-bit. Okay. And you have seen nowadays in the market, if you buy a computer system with higher bit size, they are highly priced because they give you a better resolution. Your errors will be less as you increase or less. Because my objective is to faithfully represent my machine signal. Whatever I do, I need to get back my original signal after the data acquisition system, and this is known as Xi. Okay. This is one case we have to do. Now, another related with the sampling error is this case here. So, you see I have the original black signal. If I now sample it at a lower rate or the time period is high, I will get my dashed line, which is actually a low frequency signal. So, signal is aliased as a low frequency signal. So, in fact, there is a theorem which says your sampling frequency should be greater than twice of f max to prevent signal aliasing. Okay. So, this is the Shannon's sampling theorem. So, to prevent signal aliasing, we have to do this, but the question is, many a times in this A to D devices, I have my machine here and I have a transducer. I am giving an analog signal and I have an A to D converter, which comes in the market with the sampling frequency, and then I have to put some device here so that I get no aliasing in my digital signal. So, this is of course a digital signal, okay, Xi, and this is analog, this is also analog, and this is my transducer. So, what we can do is, if I put a filter okay, so that it does not allow, there is a certain roll off cutoff frequency of this filter, such that it does not allow any frequency beyond Fs by 2 to pass on to the analog filter, because this is known to me. So, I can set this is a low pass analog anti-aliasing filter. So, if I go to the market and if I buy an A to D converter with the sampling frequency, I can always have the low pass anti-aliasing filter put as a front end before the A to D process. Some of them have, some of the A to D converters have such filters before them, or I can put an additional low pass analog anti-aliasing filter with a cutoff frequency F c is equal to F s by 2. So, that any signal which comes in, which I get Xi here, is never aliased. Okay. This is a very important thing which you have to keep in mind. So, as you know, in CBM there are many signals, for example, with time, with this is the temperature signal, as opposed to time for a vibration signal. Temperature signals do not change so rapidly, okay, unlike a vibration signal. Vibration signal could be changing very fast, but a temperature signal is very slow. Okay. So, this is a very low frequency signal. And this is the usually a high frequency signal. So, the data acquisition system A to D converters for a temperature recording conversion is actually it can have a low frequency signal sampling frequency. In fact, they are much cheaper compared to the data acquisition devices used for dynamic signals, which are vibrations. So, obviously people sometimes ask me, what is the typical frequency range of vibration signals for CBM? I say, if you look into IC engines and motors, though if I talk about the audio range from 20 hertz to 20 kilohertz, vibration signals are good up to 10 kilohertz. There is enough information to do any CBM. Temperature, even less than around 100 hertz. Okay, 10 kilohertz, very high. Now, there are few other devices. For example, you will see a lot of ultrasonics, which are used for radars, etc., sonars, etc. This is greater than 20 kilohertz. Okay, depending on some underwater acoustics application, they can go up to even 200, 500 kilohertz. Okay, particularly in some of the underwater sonars. And if you look at acoustic emission is something which we will discuss later on. The maximum frequency of this signal could be around 5 megahertz. See, you can see different signals and their frequency content. Okay, because to get a meaningful representation, they all have to be sampled at Fs is greater than twice F max. So, this has to be kept in mind. So, if you go to the market to buy data acquisition systems, you will see data acquisition systems with different sampling frequencies because of this obvious reasons. One is to prevent signal aliasing, and other is to have higher bit size, so that the amplitude resolution is fine enough. But then there are few other features of an A to D converter. One is this maximum input range. It's usually 0 to 10 volts. Polarity, sometimes whether they will be bipolar or unipolar. Gain, sometimes some of these data acquisition units, the least sensitivity or amplitude resolution is so low that even a thermocouple signal giving few millivolts cannot be sensed. So, we need to have a preamplifier to give a gain, some gain 10x or whatever 100x, so that they are greater than the amplitude resolution of the unit. Okay. Of course, nowadays this is an open loop process in which we are doing in CBM, but many of the closed loop operations wherein after you take the signal through an A to D converter, you do an analysis and you want to control through a mechanical feedback on an actuator. So, we need to have what is known as digital to analog. So, some of the units have a D2, and that is for a closed loop control systems and so on. Some of this, because finally, this system has stored the values 0, 0, 0 to 1, 1, 1. Where do I store them? I store them in the random access memory of my computer systems. Okay. Some RAM memory is required. So, if this was an 8-bit system, so each digital sample will take 1 byte of storage space. So, memory also comes with a cost. So, if I have higher resolutions, the storage space would increase, okay, and then that would lead to having more number of RAM required, because finally, this digital data needs to be stored somewhere. Okay. So, I have a bus, a digital bus onto which I put my A to D converter digital, and from this bus I can have a memory location, or I can put onboard memory. So, and this bus is an architecture which is prevalent in today's computers. So, now we started, I will talk about these different bus architectures which are available today. And then there are provisions, and we just talked about one channel. Imagine I have a machine where there are hundreds of analog output. So, some of them have to be acquired simultaneously, some of them one by one. So, in an A to D converter, simultaneously how many channels I can digitize is also a function, okay, and so on. Okay. Because the data storage would capability would reduce by having more channels, and many times you will see later on when we talk about wireless data acquisition, how this signal can be transported through Wi-Fi to another device, and what are the limitations of signal transmission over Wi-Fi frequency range and so on. Sometimes when you have one to converter, one digital converter, but there are many input, and we can have an analog or a digital switching circuit which is known as a multiplexing, okay. And then sometimes we will trigger and synchronize, and end of the day we have who's controlling all this. So, there has to be a user interface software, okay, to control all the. So, in the universities or in IITs, we have a very popular software lab, View, okay, which is out of a company, and then this is used to control the data acquisition units and communicate with the computers. And then today it was analog signals for CBM, it could be vision signals, it could be motion signals and so on. Okay. And another thing is, of course, there are many other features which are available in data acquisition unit. One is triggering. When, at what time do I need to sample a signal? So, only when a max has occurred, I will start acquisition. So, this is called as a trigger level. Only when a max has occurred or event has occurred, I will acquire the signal. Okay. So, this has to be taken into account when we are doing data acquisition. So, just to recap, there are a lot of features in data acquisition units, but most important is quantization error, which can be improved by increasing the bit size, and other is the aliasing error, which can be improved by increasing the sampling frequency or having a low pass anti-aliasing filter. Now, coming to this bus, because once I have the digital data, I need to transfer them. Of course, we used to have the GPIB transfer protocol, which had a speed of 8 megabytes per second. We had the RS-232, it is very slow, but still people use it, 232 kilobits per second. FireWire is 3.2 gigabits per second, which is very popular in the Mac systems. Today, we have the USB systems, and then there is to be PCMCIA 20 megabytes per second. So, faster computers have faster speeds. We have 3.2 today. Even in the data transfer, even in wireless communications, we are talking about 3G, 4G. People are talking about 5G. So, this is only how fast we can transfer the data. If you can transfer the data fast, you can acquire data, large number of data, store large number of data, and process dynamic signals. We will talk about data recording and data transfer later on. Okay. And then PCIA interconnect, it is a clock speed of 33 megahertz, which has replaced the ISA-ISA bus. We also use the Ethernet once the data is in digits, and of course, we have the Cat5 cable connecting devices, we have the wireless Ethernet and so on. So, today's world, be it machines, computers, mobile devices, we need faster ways of transferring digital data through these protocols which are available, and then we can do our processing and make an analysis. Of course, there are network based data acquisition systems like a client server model. So, you could be sitting somewhere and controlling your acquisition and so on. Okay. We will continue more on this in the subsequent classes. Thank you.